Okay, yesterday we started to talk about the circuit averaging techniques for deriving say, AC small signal model for switching mode power converters. Okay, so let's continue that discussion. Okay, let me share my whiteboard. Okay, this is what we started yesterday, and I just want to exemplify the process of circuit averaging by taking into account the buck boost operating in DCM. Okay, so remember the main idea. The main idea is that look at your circuits, look at the components that are responsible for, say, the variable structure, so the time variant behavior of the system, so the switches, diode and MOSFET transistors, and try to replace them by a dependent current source or dependent voltage source that take into account only the average behavior over a switching period. Okay, which circuit I have to say replace? Voltage source, current source. At the beginning of the analysis, this is not is a choice. Okay, it's not clear. One solution can say bring you to a very long road to the solutions, and the other one can be say much more simple. Okay, but anyway, we have to try. So the experience say which is the best solution. For the buck boost DCM, I can assure you that if you replace for example, the diode, okay, here with a dependent current source, which impress the average current, the same average current across the diode over a period, then the solution would be, say, something that you can manage easily. Okay, so let's start this process. Okay, so look at the current through the diode. We are operating in DCM, so you have a period Ts. T1 is the time interval in which you have the transistor which is on, and when transistor is on, the diode is off, no current flow through it. Then you have the time interval T2, and during T2 we have the switch which is off, the diode is on, no current flow through T2, T3, both the diode and the switch are off, so no current flow again. So you have this kind of triangular waveform. This triangular waveform is just a section of the overall inductor waveform. Okay, so the current through the inductor here, okay, is the same of the current through the diode when the switch is off. And so we have this similarity. So let's compute the peak value of the current through the inductor, which is, by the way, the same peak value that you have in the diode current. Okay, this peak value can be easily derived looking at the time interval T1. Okay, you have a slope, and the slope is the input voltage over L. This slope has a duration which is T1, so T1 is the duty cycle multiplied Ts. So we can easily write that the maximum current is the slope, so V in over L, multiplied the duty cycle multiplied Ts, so the time interval in which there is this slope. So V in over L, we can put Fs instead of Ts. Okay, this is the maximum value. So we found this peak value of the diode current. Now we have to derive the time interval T2, or if you want, T2 over Ts. And T2 over Ts, let me call this D2. It's not the duty cycle, is something that is dimensionless that we can call D2. The duty cycle is just, let's say, this one, okay? T1 divided by Ts. So how can you find the time interval T2? But simply you have to consider that if you have the maximum current, and if you have this maximum current, you divide by the slope of this current, then you can find out T2 interval. Okay, so Ts multiply D2. Okay, so Imax is something that I already know. The slope here is V naught over L. V naught is negative, so let me put here the absolute value. Okay, so let me change the page. I have Imax, define the divided by the slope, which is V naught divided by L. And this is d2 multiplied ds. So from this, we can find d2, which is Imax over V naught L, and then you have Fs. Okay, but Imax was previously derived. Imax is V in over L d over Fs. Okay, so I can use this Imax here, and I put there. So I have V in over L duty cycle over switching frequency, L Fs divided absolute value of V naught. And then comes out V in over V naught multiplied D. This is the duty cycle. So in the circuit that you have here, which is the buck boost converter, which is the expression of the output voltage V naught. But V naught is simply I naught multiplied R. Okay, and I naught is the current flowing to the load. Is this current here, I naught? Okay, which is say constant current, and this constant current is exactly the average value of the diode current. Okay, so I naught is the average value. So I can define I naught just by taking the average of the triangular waveform in the diode. This is the peak value, which is the 8 of my triangle divided by 2, multiplied by the base, that triangle, which is d2 multiply ts, and then you have to average over ts. So you have this expression here. Okay, so let me put I naught in this expression, and so you have that V naught is I max over 2 d2 multiplied load resistance. Then I have d2 is something that I know because d2 is given by this expression here. And then I have also Imax, because Imax is something that I derived here, is here. Okay, so now I am in the position to, say, replace all these quantities. V in d 2L Fs multiplied V in over V naught multiplied D multiplied R. Okay, so let me now rewrite here V naught. V naught is V in square duty cycle square. Then you have 2L switching frequency, V naught absolute value that multiplies R. Now let me exploit this space here. So I have V naught here and V naught here. Let me put V naught square value, which is V in square T square to LFSR. Okay, so from this expression I have to extract the root, the square root. I can find V naught. So V naught. Now, when you take the root square, you can choose between the plus and the minus sign, and the good sign is the minus. Remember that V naught is has an opposite polarity with respect to that of V in. So V naught requires a negative sign here. So this is V in multiplied D, then you have R to LFS. Okay. Then I have, remember my goal. My goal is to derive the average current ID. Okay, so I take the average current ID from this equation here. Okay, and I want to express this average current with respect to all other parameters. Okay, so the average current ID, which is I naught, which is negative V naught over R, is simply if you take the plus sign here is good enough. Okay, so let me choose between the plus and minus sign here, the plus sign here, because now if I put I naught, which is negative here, which is the correct direction, because I can have I naught, which is opposite direction of the ID here. Okay, the negative side of V naught is automatically considered. So if you put a negative sign here, then you have to put here, say, plus. Okay, but not worry about the sign. This is not something that can, say, has a role in what I'm defining here. But if you be coherent, it's better to do this. So V naught is V in multiplied D R to LFS, and then you have to divide by R. Okay, so you can take this R and within the root square, and what happens that you have V in multiplied D 1 over 2 RLFS. Okay, so ID average value is negative V in D. Now R here is simply V naught over I naught. So let me replace these. So I have I naught 2 V naught LFS. Okay, so finally we get this expression for the average current flowing through the diode, which depends on V in, the duty cycle, V naught, all the parameters that you can have in your buck boost. Let's take the square of these quantities, and so I have ID average value square, and now this is the reason why there is not so many important to the sign here, because now I get the square root, so the square of this quantity, so this minus sign disappear. V in square, D square, I naught, but I naught is ID average value, 2 V naught LFS. Okay, and if you take the sign here, the correct sign, I naught is minus ID average value. So I can have here the negative sign. Okay, so finally I have this expression here. This expression can be simplified in this way. And so finally we get this quantity, average value of the current flowing through the diode, and this quantity, I repeat, was derived in order to make evident the, say, dependencies of this current from V in, V naught, and the duty cycle. is negative sign V in square d square 1 over 2 V naught LFS. Okay? So this is the value of the current that we can use for our diode. Okay, we can replace the diode with this quantity here. So my diode is say something that can be replaced by an average current which has exactly this value. Okay, this is what can be used. Okay, remember that we are talking about average quantities. Okay, we averaged the current through the diode. Of course, we are talking about the average circuit. Okay, not just the current. I just find out an expression for this current, and I was able to derive this expression in order to make evident that, say, dependencies of this average current from V in, V naught, and duty cycle. But you have to think about that. Taking about the average of this quantity means that you are averaging all the other characteristics. Okay. For example, you can say that the voltage, the average voltage across the inductance in this circuit is null. Okay, so you can think about that this node here is connected to this one. Here you have the inductance. Okay, but in terms of average quantities, here you have to say something which is as short. So this current source here appears exactly in parallel to the output voltage V naught. Okay. Now we have this this circuit here, and I take the average of the current flowing to the diode, and I'm taking, say, I'm deriving something which is an average circuit, okay, in which all the quantity are averaged. In this situation, the circuits that derive from this analysis is a time invariant circuit. Invariant because I was able to replace my, say, switch here, the diode, with a time invariant current source, which has the average of the current through this period Ts. Of course, I'm missing the peak value of this current, the root mean square value, whatever. I just considering, say, all the what happens in a cycle in terms of its average quantity. So I lose any, say, variable structure problems. So my circuit is time invariant. Of course, this is not enough. Remember that all the methods that I described to you are based on two steps. First, to transform a time variant circuit into a time invariant circuit. And this is what happened, for example, for the circuit average. Okay, this step is performed by analysis of the circuits, find out which is the average current or average voltage, and replace the switch by, say, a current source or a voltage source. But then we have to perform another step, which is move from a non-linear system to a linear system, because this circuit, and basically this equation here, is non-linear. Okay, we have to linearize it. So, in which way we can linearize it? Okay, what I described to you up to now is something that is related to the fact that, I don't know, duty cycle is something that is small signal perturbated, like this one, and V in the same, etc., etc., etc. So I can replace this quantity inside this expression in order to derive the linear the transformation of the circuits. And this can be done. Okay, this is a possibility. You have to perturbate and then linearize, or you can apply some other methods. Okay, it can be instructive to see another way to move from a non-linear circuit to a linear circuit. Okay, and this is to apply the Taylor series. Okay, so in this case, let's apply Taylor's expansion to ID, average quantity. Just a few words about the Taylor expansion. You have a function which is function dependent on 3 variables. Let's say this 3 variables because here we have 3 variables for the average current. Then you can expand as the value of the function is now, say, DC operating point. Okay, this is a DC operating point, so x0, y0, and zeta0 are what is the stable point, okay, the DC point, plus the partial derivative of the function with respect to the first variable, x, evaluated in this DC operating point, multiplied x minus x0, which is the coordinate x for the stable point, plus partial derivative of f with respect to the second variable, again computed at the DC operating point, multiplied y minus the DC operating coordinate y, plus the partial derivative of f with respect to zeta, again computed in the DC operating point, multiplied zeta minus zeta 0, plus second order terms. Okay, so in order to get a linear model, okay, we can apply to the average current ID the Taylor series like this one. And in order to get some linear behavior, you have to neglect the second order terms. And this operation is totally, let's say, similar to the operation than we get in the previous techniques when I multiplied small signal variations among them, and I neglect the second order term. Okay, and then since we are just focusing on the variation, I also can neglect the DC contribution. Okay, and this is something that is done, for example, when I look at the small signal circuit and I say put to 0 the V in voltage. Okay, so just look at these 3 partial derivative. Okay, and I have to find out these quantities. Of course, when you get x minus x0, means that I have the variable x to which I have to subtract the DC operating point. Okay, and when I have the variable x includes DC and AC terms. But to this total variable, I have to subtract DC term. It's like that here you have, let's say, just the small signal quantity. It is the same that you can perform, for example, on the duty cycle here. This is AC plus DC, and this is just AC. Okay, so when you have AC plus DC, so D minus the duty cycle term, then you can have just the small signal variation. So this is the same difference. So you can replace this quantity to the small signal hat variable. Okay, so apply this Fourier series to ID. ID, small signal, okay, is something that is related to neglecting the second order term, means that they have, say, not the exact solution, but something which is, say, similar to that, is close enough. So ID partial derivative versus the first variable is V in, for example, and this is computed for V in, for the duty cycle, and V naught, all, say, operating point, DC quantity, multiplied V in small signal variation, plus the partial derivative of ID average value over duty cycle, again computed for V in, duty cycle, and V naught, multiplied by the hat, plus the partial derivative of the average quantities over V naught, again computed at the DC operating point, multiplied V naught hat. Okay, so we have to compute these 3 partial derivative. Let me rewrite these terms in terms of a coefficient A that multiplies V in plus B that multiplies D hat plus C that multiplies V naught. Okay, A, B, C are exactly what I'm going to derive. Let me rewrite here the expression that we previously derived for ID average value, which is this one. Okay, so now I have to derive the ID average over Vin, which is the coefficient that I call A. If you take the derivative here, you get minus 2 Vin, and the 2 simplify with this 2 here, so Vin, and then you have d square V naught LFS. The ID over the duty cycle, which is the coefficient B, and this is again duty cycle d square, so minus 2d, and 2 simplify with this 2 at the numerator here, denominator, so minus v in square d over v naught LFS, the ID average value over v naught, which is C, and this is now v naught appears here at the denominator, so you get remember that the derivative of 1 over v naught is something like minus 1 over v naught square. Okay, so this means that you have 2 v naught square LFS. Okay, so here you have the 3 coefficients. Okay, so these 3 coefficients, look at what happens here. Now I have a small signal current, okay, here through the diode, which is the summation of 3 contributions. It's like you have, let's say, in my previous model, that the original average current ID here in the average circuit can be replaced in small signal analysis by 3 sources. Okay, the source which is A V in, another source which is B duty cycle, and then other sources which is C V naught. C naught and R. Now this variable is the small signal quantities V naught. Okay, so this is the small signal. Okay, so this circuit is time invariant and also linear because we linearize it. We have ID and then this summation. So let me just get some derivation, okay, about this quantity. For example, we have 3 coefficients, A, B, and C. First of all, we have to say that since my goal is to derive what? One of the most important transfer functions, I want to derive V naught over duty cycle, okay, small signal ratio, which is our control to output transfer function. Okay, always in this and in describing these 3 methods, at the end we derive this transfer function, which is very important for control action. Okay, what is the effect of the variation of the control signal in terms of output voltage control, output voltage quantity. Okay, so my goal is here, and in deriving this quantity, I just have to consider null the variation, for example, of the input voltage V. Okay, this is something that I did in the all other techniques. Okay, when we get to the small signal circuit, always I consider the variation of V in to be null. So V in is always constant, okay? So this quantity is always considered when V in is equal to 0. So that means that my contribution, the first one, the A one, can be considered to be null. Okay, I want just to derive the relationship between V naught and T. And so in order to do that, I have to say cancel out the variation of V. In this sense, now I have circuits that have the variable, V naught variable, then I have V naught variable. So in this case, I can derive this transfer function. Okay. So focus on the B and C coefficient. Okay. You should remember that in the buck boost, the V naught over V in, which is the conversion ratio in DCM, is minus D R 2 LFS. Okay, this is the conversion ratio that we define M DCM in the previous lecture. Okay, so now I can square the first part here, and this is D square R 2 LFS. Now look at this B coefficient. Okay, we have minus V in D V naught L over Fs. Okay, this is my B coefficient. So this coefficient can be rewrite in this sense. I have V square and V in square and V naught here. Okay, so I can multiply it by, for example, V naught. I can rewrite in this V naught, V in square, V naught. Then I can have V naught over V naught here, and then D over L Fs. Okay. If you look, so I just multiplied the previous expression by V naught divided V naught. But here now I have the quantity that I previously derived, which is this one. Okay, so let me put this expression into the previous one. And then I have, let me use this V naught D LFS. And here you have D square R 2 LFS. Sorry, there is something which is not. Okay, this is V. Sorry, this is V in square over V naught square. So it's the opposite. Okay, I have to replace 2 LFS. Of course, is 2 LFS. D square R. Okay, this is V in square divided V naught square. And I have something which is 2 V naught over D. Okay, now V naught can be simply described in terms of minus D V in R 2 LFS. And so you can replace V naught with that specific quantity, so V naught is V in negative V in D 2 R 2 LFS, you get the result, which is that it comes out V in 2 LRF. So it has a quite long derivation, but this is the coefficient B. Okay, whatever route you are following, let's say you should get this result. The coefficient C, I prefer to write in this way because that, say, less. Inside there is no V naught. Okay, it's just V in. Okay, it can be something good. And now look at what happens here. You have again the coefficient C, V in square over V naught square. So something which is, say, related to this expression here. And if you get in the coefficient C, try to not have the same mistakes as before. This is D squared 2LFS. D squared 2LFS multiplying 2LFS divided D squared over R. Okay, this is again V in square over V naught square. Okay. What happens here is that you have these two quantities that are, say, cancel out, also this square, so it comes that this is 1 over R. So this is C. Okay, we simplified a little bit these two coefficients. Okay, the coefficient A is not of interest in deriving the transfer function V naught over D. B and C are of interest, okay? So the coefficient C in particular say that this is the same of 1 over R. So you can replace C with 1 over R. So as you can see here, you have a current source, which current is V naught over R, okay? So we can replace this current source by the component that has the same characteristic equation. And the component that has the same characteristic equation is a resistance. So you can replace this circuit here by a resistance R. Okay, because the resistance R are a current across it, which is exactly, this is V naught, and the current is V naught over R. So this component here acts exactly my coefficient of the current, which is C. Okay, this is R, and so we have 2R in parallel. So I can collapse the two resistance into 1. One of these resistance comes out from the coefficient C, the other one is the load. Okay, then you have C naught, and then you have the remaining current source, which is the coefficient B, which is V in, we derived before, square root of 2 RLFS multiplying, and the coefficient B is multiplying the duty cycle. And this is V naught. Okay. As you can see here, the method is totally circuital method. Okay, so you have to, say, do some computations, and then you have to derive the correct expression. But now we are just finish our work because we have a circuit in which I have V naught, and the source depends on D. So easily I can derive V naught over D, which is my transfer function, control to output transfer function. How can you derive this one? This is, let's say, simple given is minus the source, which is V in 2 RLFS square root, which multiplies the, you have here the parallel of half R and 1 over C naught. Okay? So this is minus V in 2 RLFS, and this is 1 over 1 plus S C naught RF. This is my transfer function. Of course, we are in linear circuit, time invariant linear circuit, so I can apply the Laplace. And so this is exactly what I did. So I have a gain, which is this one, and this is exactly the, say, the gain that I derived in steady state analysis of the buck boost. Okay. And then I have here a pole. Single pole, not complex conjugate pole. Single pole, and this is the gain. The pole depends on the product C naught multiplied R divided by 2. So if you want the frequency of the pole is 1 over 2 P C naught RF. So this is 1 over P C naught R. This pole is moving. It's moving because it depends on the R, and R is not fixed at all. Okay, it can change during the operation R. So this is a pole which is a moving pole. The gain is given by this expression here. Okay, is the constant value. And then what happens? Here we have not considered the ESR. If you consider the ESR here, you have to restart your, say, computation from the beginning, etc. No, you have just to apply the ESR here and to derive the new expression. V naught over D, which is now minus V in R 2L RFS let me derive this expression, okay, just because I have a doubt. This means R and F multiplied 1 S C naught, R and F plus 1 C naught, okay? So it means that you have R over 1 plus S C naught R, okay? Is okay, if you, when you get, so in order to have 1 here, you have to multiply his 1 divided by 2. So when you get this 1 and you take these equations into the gain, then you have exactly that it comes R over you get, sorry, there is an error in the slide, I think. This is what here, then you get R inside, so this is R here. I think this is correct, 1 over 2 LFS without this one. I have to check, but it is not very. S C naught plus So you get 2 here. Yes, this is exact. So you have R divided by 2, and this is 2. Okay, good. I forgot there is the 2 here. 2 and R. So when I put R here, it becomes, let's say, R at the numerator. Then I have the 2, and the 2 becomes 2 here. Okay, so the gain is, let me put here, minus V in R over 2LFS. Okay, this is the gain we have in the, and then you can cancel out this. Okay, so I think that the slides are not correct, so I have to correct them. Okay, so this is R over 2LFS. Now, okay, we can continue. If you have the ISR here, then you have to take that now we have also a 0. And what happens with the denominator? The denominator is something like S naught R and F plus ESR. Okay, this is the correct version with the ESR. Of course, the ESR typically is well less R divided by 2, so we can write down this one in minus V in R over 2LFS 1 plus S C naught ESR divided 1 plus S C naught R and F, like before. Okay, so now we have the same gain, the same pole as before, but then we have another 0. So you have F zeta, which is 1 over 2P C naught ESR. You have a pole, which is 1 over P C naught R, and you have the gain, which is minus negative V in R over 2LFS. Okay? So, a fixed 0, which is fixed because C naught and ESR, when you say find out your electrolytic capacity, they are not moving. This is a moving pole. Okay? And this is the gain. So now, with respect to the back, for example, CCM, in which you have 2 poles and 1 0, then you have just 1 pole and 1 0. This is the transfer function we have to study for design the controller of these circuits. Why we have just 1 pole instead of 2, like, for example, as I said, in the back CCM? But you have to understand that anytime you have a pole in a system, in a, say, dynamic system, that pole is related to reactive elements inside that circuit, okay? Elements that are able to store energy, okay? For example, inductors store energy into the magnetic field surrounding the inductor, and capacitor into the electric field. So, if you look at what happens in a, say, DCM converter, any DCM converter, so this happens also for the boost DCM. Look at what happens to the, let's say, the state variable in the inductor, so the current flowing to the inductor. This current is something like this. Okay, this is DCM, so it means that you have T1, and then you have a time interval T2, and this is TS. So you can see here, and look what happens in this period TS. What happens in this period TS is that all the energy that is stored into the inductor, okay, is released by the inductor before the end of TS. Okay, the energy isn't, say, included in this area here. Okay, and this area here goes to, say, the current goes to 0 before the end of TS. It means that when you end this cycle, and this happens for any cycle in DCM, there is no residual energy in the inductor. The inductor, all the energy that is stored, it releases in the same cycle. Remember that when we talked about the DCM, buck boost, or the boost, we derived the conversion ratio, V naught over V, exactly looking at, say, taking some energy consideration. Okay, we computed the energy in the charging phase of the buck boost, and then we say that since all this energy, which is acquired during the charging phase, is discharged into the successive phase, we are able to, say, define, to equate the charging energy with respect to that it is discharged and to find out the conversion ratio. Okay, remember, look at that slide, the way we derived the conversion ratio m/dcm for the buck boost. Okay, because we exactly employed some energy consideration. Okay, and that consideration said that all the energy that is say stored, it is released in the same interval. This happened the same. Okay, there is another way, no memory, cycle by cycle, what happens in the previous cycle. Okay, this not happens in CCM. CCM, the inductor, which is storing the energy, is not completely released by the inductor in the same cycle. If you have, let's say, a CCM, the current goes in this way. Okay, so this cycle, the second cycle here, starts exactly when the first cycle ends. Okay, if the cycle is not exactly here and changed, the successive cycle is has to start when the previous cycle ends. So there is a memory in a certain cycle to the energy which is stored in the previous cycle. This not happen here. So this fact means that the memory elements are not exactly something that store memory cycle by cycle. This, say, consideration that it's totally qualitative, is not, say, so detailed, brings to the fact that there is the pole due to the inductance, okay? But the pole due to this inductance is so fast that comes out, let's say, for frequency higher than 1/2f switch. And remember that my small signal model, our maximum frequency value is valid up to 1/2f switch. Okay, this not happen here, so the poles of the inductor do not appear here. There is only the pole of the capacitor, but there is no inductance in this equation. Okay, L is disappearing here because due to the fact that the pole is very fast, you can say. That is over, say, the a possible pole of the inductance occurs for frequencies that are higher 1/2fs, in which the model cannot be more valid. Okay, and this is due to the fact that the memory characteristic of this reactive element is lost when the cycle terminates, basically. Okay, so it's at very high frequency, and this frequency is not modeled by this equation here. So no inductance pole is included here. Okay, in CCM always happens that you have two poles because you have two reactive elements, inductance and the capacitors. Okay, here in DCM, and this happens for all DCM circuit, not just the buck boost. The same is for the boost, and the same is also for the buck. In DCM, there is this, let's say, missing pole due to the inductance, just that due to the output capacitor. Another question that can be explained here is why in DCM we have no more the right half plane zero. Okay, as you can see here, the pole at zero that you have here is a left hand plane zero, so it's a good pole, good zero. Sorry, there is no more the behavior. So why in the buck boost there is no this kind of zero? In other terms, look at the output circuit of a buck boost. If you have the buck boost, the output side is exactly the same output circuit you have in the boost. Okay, so output, not circuit, but better to say output side of a buck boost is that of the boost. Okay, you have the diode here. Okay, the polarity is changed, but is always a diode here, and then you have C naught and R. But remember what I said about the position of the diode here in the boost, that this is responsible for, say, the right half plane zero of the boost operated in CCM. Because if you want to increase the duty cycle in order to increase the output voltage, okay, then you have to delay the turn on of this diode. Okay, if you have to increase V naught, you have to increase the duty cycle, but then when you increase the duty cycle, you are slightly delaying the turn on of the diode. So there is a time interval which is larger than before, in which the output capacitor C naught have to hold the output voltage. Okay, so it means that if this time interval is large, then V naught, instead of rising at the initial time instant, is decreasing. So if you look the output voltage V naught, if this is duty cycle, if the duty cycle, say, rise up in this, V naught has a variation which is negative, and then it increases. Okay, and this behavior is typical of a right half plane zero. But then in the buck boost, we have the same output circuit, but there is no right half plane zero in the transfer function. So something that is not exactly the same occurs here. So in the buck boost, look at the diode current. The diode current in DCM is this one. This is TS. So here the switch is on here during T1. Okay. Then I have another cycle, okay, which is the same, etc. Now, suppose that my output voltage is decreasing, so the control, the feedback, understand that the output voltage is decreasing and immediately rise up the duty cycle in order to, say, compensate this variation, because I want to get output voltage V naught to be constant. So in order to do that, I have to enlarge the time interval in which the switch is on. And so I get another time interval. Okay, now my T on is larger than before, okay, because I increased the duty cycle. So that means that, again, as happened in the boost, I delay the turn on of the diode, because when the switch is on, okay, the diode is off. So the diode starts to be on here, okay, in this point. So we have a delay. During this delay, the diode is again off. And if the diode is off, then it is, let's say, is the output capacitor C naught, which is in charge to provide the charge needed for the output voltage to remain constant. Okay, but this time interval here can induce the output voltage to reduces. Okay, so what happens here is a matter of how much this interval is large. Okay, in a DCM, this quantity here, let's say we have 3 time intervals. Okay, we have T1, then we have T2, and then we have T3. So this delay here is a small fraction of the total TS interval here. In CCM, for example, what happened is that you have just T1 and T2. So this time interval here, the time interval which the diode is on, this can be a large part of the total TS. In other words, the delay that you can have in DCM due to the increasing of the cycle here is much smaller than that you can have in CCM. It's so smaller that the right half plane zero happens for frequency that are larger than, again, 1/2 Fs. And so it is not modeled by small signal technique. So the right half plane zero is always there because there is the behavior due to this diode. okay, which is delayed in its, say, turn on. And so there is a larger time interval in which the capacitor should, say, hold the same voltage, so it can discharge. But this time interval here is much smaller than that you can have in CCM. So while in CCM, buck and boost, you have the zero in the right-hand plane, and so basically no way to operate the boost and the buck boost in CCM. In DCM, you can operate both the buck boost and the boost because this right half plane zero is moved to very high frequency due to the fact that this time interval is, let's say, not so huge. Is a qualitative, let's say, explanation. Okay, if you want to get more detailed mathematical description, okay, you have to compute exactly what happens in terms of, let's say, modeling of this frequency behavior. Okay, so I hope that this little bit clarify why we just have some behavior in DCM and not having CCM. Of course, this can raise several questions. So if you want to say, if you have questions, I'm here to answer that. Okay. Questions about what I derived here? Maybe some problems, issues? Some of my explanations are just, let's say, qualitative and not quantitative, okay, in order to understand what happens. In the next hour, I will summarize for all students, also mechatronics students, what we derived, okay? So in order to, say, start from some knowledge about the control to output control function, B naught over D, because from that control function, we can start the design of the control. So I would summarize all we derived for, say, to be something good for all students. If you have no questions, I can stop here this virtual classroom. Okay, I terminate my virtual classroom here. I can start another virtual classroom at 10, okay, for all students. Okay, so you receive another invitation to another virtual class with a different title. Okay, good. See you at 10, so a quarter of an hour from now.